origins and invention. During the First World War, the battlefield changed faster than anyone expected. Machine guns ruled the trenches, but they were still firing the same ammunition as ordinary rifles. When the first armored tanks and aircraft appeared, it became clear that the old calibers no longer had the power to stop them. General John Pershing, commander of the American Expeditionary Forces, demanded something new, a machine gun powerful enough to destroy these armored threats. He wanted a weapon that could fire a half-inch projectile at over 2,700 feet per second. The task fell to John Browning, already America's most trusted gun designer. Browning began by scaling up one of his most reliable designs, the M1917 water-cooled machine gun. He enlarged every component to handle a much bigger round, one that didn't even exist yet. Engineers developed that new cartridge specifically for the project, a rimless, high-velocity bullet inspired by the top 3206 rifle round and partly by captured German 13.2mm anti-tank ammunition. The result was the Top 50 BMG, the 12.7 99mm cartridge that would become legendary. When the first prototype appeared in 1921, it was officially known as the M1921. It was powerful, but also a beast to handle. The water-cooled version weighed about 120 pounds, the air-cooled around 84, and the tripod another 44. Infantry couldn't move it easily. Small aircraft of the time couldn't carry it, and its fierce recoil made accuracy difficult. At first, it seemed like an impressive but impractical experiment. John Browning died in 1926, but his design lived on. Engineers refined it, reworking the feed system so it could be switched from left to right, and creating a universal receiver that could accept different barrels for different purposes. With those changes, the weapon evolved into the M2 Browning, lighter, more flexible, and ready for mass production. While other nations were developing heavy 20 and 30mm cannons, the United States believed the .50 caliber's high velocity and versatility would be enough, and they were right. The M2 could be mounted on vehicles, ships, aircraft, or simple tripods. It could shoot down planes, tear through armor, or defend a convoy. What began as a response to the limitations of the First World War had quietly created one of the most enduring weapons in history, a machine gun so powerful, so reliable, and so adaptable that it would go on to shape every major conflict of the century and still serve on the battlefield 100 years later. Early prototypes. During testing and early service, the .50 caliber started life as a formidable but awkward monster. The first production model, the M1921, was effectively a scaled-up heavy machine gun designed for anti-aircraft work, and its size showed the water-cooled version weighed roughly 120 pounds. The lighter air-cooled variant still sat near 84 pounds, and the tripod added another 44. With belts of heavy plug AP-2 50 rounds stacked nearby, a complete ground setup could easily tip the scales well over 130 pounds. That mass mattered. Infantry squads found the weapon difficult to move, position, and sustain in the kind of fast, short-range firefights that defined much of interwar and early World War combat. Smaller aircraft and lightly armored vehicles were often unable to accommodate the gun's bulk, and early turret mounts were awkward. The feed was configured to one side, limiting how it could be installed and operated. Recoil was another real problem. Firing a half-inch high-velocity cartridge produced brutal impulses that made accurate long bursts hard to maintain from field mounts. Combined with the weight and the amount of ammunition required, the M1921 felt unwieldy as a general-purpose infantry weapon. In practice, its greatest early value was in fixed roles, coastal anti-aircraft emplacements, and shipboard mounts where weight and mobility were less important and sustained firepower was essential. The obvious potential was tempered by these logistical and ergonomic drawbacks. For a time, it looked less like the future backbone of heavy automatic fire and more like a specialized tool with limited applicability, devastating when employed correctly, but impractical in many common battlefield situations. Later refinements would address those shortcomings, but in its first incarnations, the .50 was undeniably powerful and undeniably cumbersome. Post-Browning refinements. After John Browning's death in 1926, the weapon he had begun did not stagnate. It entered a new phase of practical refinement that turned an impressive prototype into a truly versatile and reliable combat system. Engineers and ordnance officers examined every limitation the M1921 had shown in service. Excessive weight for man portability, awkward mounting solutions, one-sided feed that restricted installation, and the need to support widely different roles from shipboard anti-aircraft to aircraft guns and vehicle mounts. The solution was not a single dramatic redesign, but a series of pragmatic, interlocking improvements that multiplied the gun's usefulness. One of the first breakthroughs was rethinking the feed mechanism. Where earlier models were effectively fixed to feed from one side, the later design allowed the feed direction to be changed quickly by swapping the top cover and a few internal parts. This may sound small, but it removed a major installation constraint. Crews could now mount the gun where space and ergonomics demanded, not where the feed dictated. That flexibility drastically simplified vehicle and turret integration and reduced the time and labor needed to reconfigure weapons between platforms. Equally important was the development of a universal receiver and a modular barrel concept. Rather than building entirely different guns for different roles, engineers created a common core, a receiver that would accept several barrel assemblies. A heavy air-cooled barrel provided sustained fire and durability for ground and vehicle mounts. A lighter short-barrel aircraft version allowed higher rates of fire while saving weight aloft, and where sustained bursts were required, water-cooled jackets could still be fitted. This modularity meant logistics and training became simpler. The same basic gun could be adapted to ship, tank, truck, aircraft, or tripod with far fewer unique parts, and crews could swap components in the field or at depots. Internals were also refined. Small changes to the locking and extraction systems improved reliability under combat conditions, and more robust manufacturing tolerances reduced stoppages. The gas and recoil characteristics were smoothed by adjustments in springs and buffer geometry, which made the weapon more controllable and extended service life. Mounting adapters and more practical tripod and pintle designs were introduced so the weapon could be fired effectively from a variety of emplacements without sacrificing crew safety or mobility. These engineering choices had tactical consequences. Suddenly, the gun that had once been too bulky for most uses could appear wherever commanders needed heavy automatic fire on tanks and half-tracks as an anti-personnel and anti-aircraft defense, on aircraft as a potent armament combining range and kinetic impact, on naval mounts for ship defense, and on bipods and tripods for static defensive positions. Production planning shifted from a single-purpose prototype to mass manufacture, and doctrine evolved to exploit the M2's reach and stopping power. By resolving feed, modularity, and reliability problems, the refinements after Browning's death transformed a promising but impractical weapon into the M2 Browning, a platform valued not for one role, but for its ability to serve many. This adaptability is what allowed the gun to be produced at scale, integrated across almost every branch of service, and ultimately to become one of the most enduring small arms platforms in modern military history. WW2 deployment. By the time the Second World War began, the .50 BMG had matured from experimental hardware into a weapon that would be seen almost everywhere. Allied forces fought. It was no longer a single-purpose oddity. The M2 found roles on aircraft, ships, tanks, half-tracks, jeeps, and on tripods with infantry crews. A true multi-role machine gun whose presence changed how engagements were fought. In aircraft, the gun was adapted with lighter barrels and tuned for a much higher cyclic rate, typically pushed between roughly 500 and 1,200 rounds per minute, depending on the mount and purpose. That higher rate mattered. Air combat offers only brief windows to hit a passing enemy, so more rounds in a shorter time increased the chance of destructive hits. Heavy U.S. bombers and fighters carried large numbers of M2s. Some bombers carried over a dozen in defensive turrets, while fighters often had multiple wing-mounted guns, concentrating substantial kinetic energy on any attacker in mere seconds. When several 50s fired simultaneously, they could punch through engine housings, fuel tanks, and other vulnerable points on enemy aircraft. On the ground, the M2's long-range high-energy rounds made light fortifications and thin armor suddenly much less protective. Infantry could no longer rely on simple brick or timber cover at medium ranges. Sustained bursts could collapse walls, shred sandbag positions, or pass cleanly through unreinforced shelters. Vehicles that had been considered safe from rifle-caliber weapons now needed to account for the .5 soft-skinned trucks, armored cars, and the thin top armor on many tanks were all vulnerable. That combination of reach and destructive capability made the M2 an ideal general-purpose heavy machine gun for strafing, anti-material tasks, and convoy defense. Because of this versatility, commanders mounted the M2 everywhere they could. It became standard as a pintle gun on jeeps and half-tracks for anti-personnel and anti-aircraft defense, a roof or turret-mounted weapon on tanks to deal with aircraft and infantry threats, and a primary defensive armament on ships and bombers. The practical effect was pervasive. By mid to late war, almost every vehicle or emplacement that could carry a 50 did so, forcing enemy tactics to change. Low-flying attackers found strafing runs far more dangerous. Ground assaults now had to contend with heavy automatic fire that reached and damaged critical systems beyond what earlier machine guns could do. Production scaled to match the demand. Millions of M2s and huge quantities of 50 ammunition were manufactured, spreading the gun across every theater of operations. Its ubiquity meant that the Vivating Strafen was not just another weapon in the arsenal, it became a defining element of Allied firepower. one that reshaped both defensive and offensive tactics on land, sea, and in the air. Mad Deuce, power and tactics. They called it Mad Deuce, a nickname that captured both respect and a kind of savage familiarity. The .50 wasn't merely louder or heavier than rifle-caliber machine guns. It represented a different class of force. A single .250 BMG round delivered between 5 and 10 times the kinetic energy of the typical infantry cartridges of the era, and that translated into effects that were tactical as much as ballistic. At the squad and platoon level, the presence of a .50 changed how soldiers thought about cover, movement, and exposure. Thin walls, wooden shacks, and sandbag revetments that had sheltered men from rifle and light machine gun fire no longer guaranteed safety. A concentrated burst could punch through masonry, shred sandbags, or turn a shelter into rubble. Troops learned that being under direct .50 fire meant either rapid displacement to avoid being cut down or relying on obstacles substantial enough to stop heavy rounds, obstacles that were often impractical in forward positions. On vehicles and armor, the effects were equally disruptive. The .50 could disable optics, jam turret mechanisms, rupture fuel lines, and tear through radio housings and thin engine covers. Even when it couldn't penetrate main tank armor frontally, side and rear arcs, roof plates, and exposed components were vulnerable. That capability forced commanders to modify vehicle layouts, increase armor protection where possible, and adopt different approaches to reconnaissance and close support maneuvers. Psychologically, Mad Deuce had an outsized impact. Its distinctive crack, muzzle blast, and the visible damage it inflicted marked anyone caught in its path as the immediate priority target. Snipers would stalk its crews, mortars would bracket its emplacements, and tanks would be directed to neutralize it. That attention made 50 crews both powerful and precarious, able to shape a battlefield but constantly hunted in return. Tactically, armies adapted. Assaults that once favored rushes or simple infiltration now required suppression with indirect fire, flanking maneuvers, or calling in armor and artillery to remove the threat. Defensive doctrine shifted too. Commanders dispersed likely firing positions, concealed them better, and integrated the 50 into combined arms teams rather than treating it as a lone heavy gun. In short, Mad Deuce didn't just add firepower, it forced a rethink of protection, movement, and engagement across the front. Mechanical design. Mechanically, the M2 Browning stood apart because of how it operated. While many machine guns relied on gas systems or blowback action, the M2 used a short recoil principle, a design that helped control its immense power and ensured reliability under extreme conditions. When a .5 BMG round was fired, the barrel and bolt were locked together and moved backward as one solid unit, absorbing the initial force of the recoil. During this brief, violent movement, only about 10 millimeters, the cartridge case remained supported within the chamber, while pressure was still dangerously high. Then, as the barrel halted, the bolt continued rearward alone, extracting and ejecting the spent case before the recoil spring drove it forward again to chamber the next round. As long as the trigger was held down, that entire sequence repeated in fractions of a second, an elegant cycle of force, containment, and precision. This short recoil operation offered several crucial advantages. It prevented the thin brass cases from rupturing under pressure, drastically reduced the risk of jams, and made the weapon astonishingly durable despite the power of its ammunition. It also allowed for consistent accuracy during sustained bursts, a major improvement for a gun that fired a half-inch bullet weighing nearly 2 ounces at more than 2,700 feet per second. The M2's mechanical simplicity was deceptive. Every component from its bolt lugs to its recoil buffer was designed with precision tolerances to handle thousands of pounds of chamber pressure without distortion. It was this engineering robustness that allowed the M2 to serve across deserts, jungles, frozen mountains, and ocean decks without fundamental redesign. Soldiers learned to trust it because it worked, and when it failed, it could be stripped, cleaned, and rebuilt with basic tools in the field. For mechanics and armorers, the M2 represented the perfect balance between brute force and mechanical intelligence, a gun that seemed overbuilt yet never wasteful. Its operation wasn't a chaotic spray of fire, but a deliberate rhythm of motion and recoil, finely tuned by the laws of physics and the mind of a man who understood them better than anyone, John Browning. German perspective. The Germans feared the 550 for more than its noise. They feared what it could do and the way it changed the battlefield. The 50 BMG delivered between 5 and 10 times the energy of standard infantry cartridges, and that translated into effects ordinary rounds could not produce. Thin masonry, timber shelters, and sandbag revetments were no longer reliable cover at medium ranges. A sustained burst could punch through walls or shred protective positions, leaving defenders exposed where they once felt safe. Against vehicles and tanks, the threat was practical and immediate. The 50 could disable optics, sever radio and electrical housings, rupture fuel lines, damage tracks and suspension components, and occasionally penetrate thinner side or roof plates. Even when it failed to punch through main frontal armor, it could render a vehicle tactically useless by knocking out periscopes, radios, or by jamming turret mechanisms. In the Pacific, lightly armored Japanese tanks were especially vulnerable. Repeated accounts show how concentrated 50 fire could stop or disable these vehicles long before a larger gun was needed. There was also a powerful psychological effect. Crews and infantry who saw what a half-inch round could do learned quickly to treat any position with a mounted 50 as a high-priority target. That attention meant 50 crews were routinely hunted. Snipers, mortars, and tanks were directed at them first. Their muzzle flash, smoke, and distinctive report marked them out on the battlefield, turning a position that could dominate a sector into one that had to be neutralized, fast. A wartime myth grew around the weapon's lethality. Some claimed it had been banned by international law because of the gruesome injuries it caused. That is not true. No Geneva Convention ban existed on calibers such as the 50. The wounds it produced were severe, and witnesses often described horrific effects, but the legal prohibition rumor was a misconception rather than fact. Faced with the American 50, German forces adapted. Direct frontal assaults became far riskier. Infantry attacks increasingly relied on snipers to pick off gunners, on tanks or armored vehicles to overrun positions, or on indirect fire, mortars and artillery, to suppress or destroy emplacements. Germans also recognized the round's effectiveness. Captured M2s were sometimes reused, and production of compatible ammunition occurred in limited cases. Yet they never fielded a true equivalent in widespread infantry service. Their closest heavy automatic weapon was an aircraft or vehicle-mounted 13mm, and their standard ground-based machine guns remained rifle-caliber designs. In short, the T-50 didn't simply add a bigger bullet to the arsenal, it forced doctrinal changes, altered defensive construction, and shaped the priorities of both attackers and defenders across every theater where it was used. Ammunition evolution. The .5's versatility came not only from the gun that fired it, but from the wide range of ammunition types developed for different jobs. The basic combat round was a full metal jacket ball cartridge, heavy, fast, and capable of delivering massive kinetic energy at long ranges. But ordnance officers quickly realized that a single cartridge type could not meet every battlefield need. Armor-piercing rounds were developed to defeat hardened targets. These used hardened cores, sometimes steel, later tungsten, designed to punch through up to an inch of hardened steel at combat ranges. Against aircraft or lightly armored vehicles, AP ammunition could sever critical components or penetrate engine blocks and structural members that lighter bullets simply could not touch. Incendiary rounds added an incendiary compound in the projectile's base so that when they hit fuel tanks, oil systems, or fabric aircraft skins, the hits could ignite fires. Combining incendiary and armor-piercing characteristics produced API rounds that both penetrated and then ignited internal components, especially deadly against aircraft where fuel and oxygen were abundant. Tracer elements were often incorporated, either built into the round or loaded as a pattern in a belt, giving crews a visual reference to adjust aim during long bursts or aerial engagements. Belts were typically loaded with mixed compositions depending on the mission. For ground use, a common pattern might include ball and tracer rounds with a tracer every fifth cartridge to help the gunner see where the bursts were landing. Air-to-air belts often mixed armor-piercing, incendiary, and tracer rounds so that a hitting burst could both damage critical structure and reveal aim corrections to the gunner in the sliver of time a target remained in range. The .9 fabricerat of teld. The moati regestet thetanon in a letter lidi common solblet, what have a drefa rotoplane d-stims, 50's effective reach. With lethal energy retained well past a kilometer and useful ballistic effect beyond 2 kilometers in some configurations, made these mixed belts tactically valuable. As technology advanced, more exotic and specialized projectiles appeared. The Raufoss multi-purpose round combined an armor-piercing tungsten core, a small explosive charge, and incendiary filler. On impact it could penetrate armor, fragment, and ignite, behaving in many ways like a compact autocannon shell inside a 5-deck-sized package. The SLAP Saboted Light Armor Penetrator family used a sub-caliber high-density penetrator inside a discarding sabot to achieve very high sectional density and velocity, dramatically improving penetration against light armor and helicopters. SLAP and similar rounds delivered cannon-like armor defeat from a small arms platform, but at a higher cost per shot, which limited their routine use to specialized tasks. Specialized sniper and anti-material roles also emerged from these developments. The .5D's energy and long-range capability made it suitable for engaging material targets and distant optics, and eventually inspired anti-material rifle designs. Field experiments where machine guns were fitted with optics and fired single-aimed shots demonstrated the round's capacity for precise long-range effects, and later purpose-built rifles chambered for 50 BMG delivered that capability in a more accurate man-portable package. The tactical upshot was clear. By changing the projectile, the same gun could be a precision long-range penetrator, an anti-aircraft incendiary weapon, an anti-material standoff rifle, or a devastating anti-personnel burst weapon. Logistics adapted by fielding standardized mix-load belts tailored to mission type, and ordnance bureaus continued to refine projectile chemistry and metallurgy to squeeze new capabilities out of the same timeless cartridge. New weapon concepts? The .5 VD BMG did more than redefine medium machine gun power. It inspired new weapons concepts and configurations that multiplied its battlefield effects. One of the most literal answers to the problem of not enough bullets in a short window was to simply add more guns. The quad .5 VD BMG var in de bednamstoorden cavity benauwd kan de 54 M2s mounted together became an expression of that logic. Multiply the volume of fire to increase hit probability against fast-moving aircraft, and to produce utterly devastating firepower against ground targets. The quad mount provided a much higher effective rate of fire, dramatically increasing the number of projectiles sent downrange each second, and turning a defensive emplacement into an area denial system that could shred light vehicles, infantry concentrations, or attacking aircraft. These multi-gun mounts were not abstract exercises. The M45 quad mount and similar systems were fielded in anti-aircraft and convoy protection roles, fitted to ships, static defenses, and later to trucks and other vehicles protecting long supply lines. With electrical traverse and elevation, and with crews trained to lay down saturation fire, a Quad 5 could overwhelm a strafing attacker or break up an ambush before it closed. When Allied air superiority reduced the risk of enemy planes, commanders repurposed these mounts for direct fire support on the ground, and the results were often brutal and decisive. The same principle, more barrels, more hits, also helped inspire local improvisations. Convoys and forward units routinely mounted multiple Quad 5s on trucks, creating highly mobile, hard-hitting platforms that could counter both aircraft and insurgent attacks. The dot and barrels, 5's intrinsic power also crossed over into the world of precision and anti-material roles. Field experiments showed a simple fact. A half-inch high-velocity round could do for equipment what larger cannons did for structures. Legendary examples from later conflicts demonstrated that with the right sighting and a steady hand, a 5 quad could disable engines, optics, and other vital components at extreme ranges. Those experiments fed a different line of evolution, the idea of harnessing .50 BMG performance in a single-shot, highly accurate rifle. That lineage can be traced from unconventional field adaptations to purpose-built anti-material rifles. In one famous case, a Vietnam-era sniper adapted a Browning machine gun with a telescopic sight and scored long-range precision hits that exposed the cartridge's potential for deliberate aimed fire. Those early successes inspired firearm designers to create dedicated rifles chambered in Peak 50 BMG that combined long-range accuracy, heavy penetration, and the ability to defeat hardened or delicate targets from standoff distances. The result was a new class of weapon, heavy, unwieldy by small-arms standards, but devastating against vehicles, radar arrays, parked aircraft, and critical infrastructure, and eventually iconic designs like the Barrett M82 family, which brought anti-material capability into widespread military use. Finally, the .50's role was magnified when engineers and tacticians combined its raw power with mounting innovation. Whether in quad mounts, vehicle pintles, aircraft arrays, or precision rifles, the cartridge's energy and range allowed it to perform tasks that once required multiple specialized systems, from suppressing air attacks to disabling engines at long range, and from convoy defense to specialized sniper missions. The .50's adaptability created new doctrines and new platforms, each one extending the influence of a cartridge that began as an answer to the armored challenges of World War I. Legacy and longevity. The story of the .50 caliber Browning did not end with World War II. It simply refused to die. Most weapons born in the 1910s or 1920s were long obsolete by the jet age, but the M2 remained. It evolved slowly, incrementally, almost stubbornly, because its core design was already close to perfect. Every decade brought small refinements, a new mount, a better sight, an improved barrel change system, but the fundamental mechanism, the short recoil cycle conceived by John Browning, stayed the same. In Korea, the .50 reappeared everywhere, on tanks, on aircraft, in static defensive lines where its reach and reliability proved invaluable. In Vietnam, it served again, this time not just as an anti-aircraft or vehicle weapon, but as convoy defense and infantry support. Soldiers mounted them on trucks, riverboats, and temporary emplacements, creating the now familiar image of a gunner standing exposed behind an M2, sweeping fire through dense jungle or down a road. Those gunners were both feared and targeted. Their muzzle flash and unmistakable thunder made them magnets for enemy fire. Only decades later did designers finally introduce armored shields and then remote weapon stations that allowed operators to fire from within the safety of their vehicles. As technology advanced, the D-50's adaptability only grew. Modernized mounts added stabilized platforms, laser rangefinders, night vision, and thermal optics. Remote stations gave operators precise control through cameras and joysticks, keeping them protected while maintaining the weapon's reach and authority. New materials improved barrels, suppressors reduced muzzle flash, and smart sighting systems turned a century-old design into a platform fit for 21st century combat. The most visible evolution came with the M2A1 variant, a refined version featuring a quick-change barrel, flash suppressor, and manual safety. But the lineage is unmistakable. Every M2A1 still operates on the same principles, with the same cartridge dimensions and almost the same internal geometry as Browning's prototype from over a century ago. It is remarkable that two of the most enduring machine gun designs in history, the American M2 and the German MG42, both originated in the same era. Yet the M2 is older still, born from the final years of World War I, and it continues to serve across the world. A gun that began as an experimental answer to new armor became one of the longest-serving and most respected weapons ever built. The longevity of the .50 caliber Browning is not just a story of engineering excellence, it is a testament to functional perfection, a design so effective that no war, no technology, and no generation of soldiers has managed to replace it. Over a century later, Mauser still speaks with the same voice, heavy, deliberate, and absolute.